Good afternoon everyone. Welcome back to laser technology session. In the last class we have discussed about the different laser resonators. So we are taking a simple resonators using a two mirror system, and we studied with the concentric as well as confocal and planar and spherical mirror combinations. And now, so this configuration is plane mirror and the spherical mirror resonator, and we have get the R. So R of the mirror M2, so that we got from the previous equations. So that is L into 1 plus pi omega naught square whole square by lambda L. So your R2, we get this equation. From this equation we get the W naught. So the W naught is the beam width of the Gaussian mode in the laser cavity. And now you see this configuration, your laser mode or your Gaussian mode is infinite curvature, radius of the curvature at the plane mirror. So that means your Gaussian beam focus at the plane mirror M1. Okay, and also we have discussed what happens when L is greater than R. When L is greater than R, your W naught becomes complex, so this resonator cannot support a fundamental mode. Okay, so that means if L is greater than R, this type of resonator are unstable. So by increasing R, we can get the W naught higher values. So when you have a higher W naught, you have a larger volume at the focus. So when there is a larger volume, so that means it can interact efficiently with the amplifying medium. So that region you call a mode volume. So in general the mode volume has to be higher for the high power lasers. To get high powers, should have one of the condition is it should have larger cavity mode volume. Okay, so in the last session we discussed about the Gaussian mode in general spherical resonator. So now we are talking about a general resonator, so which is having a radius of curvatures R1 and R2 and the cavity length L. So the focus or your W naught of your this mode will be at any position of your cavity, because we don't know what is R1 and R2. So now we are trying to get the stability condition for the general spherical resonator. So now your R of Z equals to Z into 1 plus pi square omega over 4 by lambda square Z square. Similarly R of Z1, we know this is R of Z. So your Z is the position along G direction, that is propagation direction of the laser beam. So now R of Z1 equals to, you substitute Z1 instead of Z, so you will get this expression. And similarly your radius of curvature of the mirror M2 is same as the radius of curvature of Gaussian mode at the M2 is nothing but Z2 into 1 plus pi square omega naught power 4 by lambda square Z2 square. So now I am defining this k square as this term, the pi square omega power 4 by lambda square. So this term is defined as a k square. So now, and also I am choosing a sign conversion that a radius of curvature is taken as a positive when you are going in the direction towards the resonator. If a concave surface appears, then it is taken as a positive. Now you are going in this direction, this appears as a convex surface, that's why you are taking a negative. Then is propagating this direction, it appears concave surface. So this is just a simple sign conversion. So now your R of Z2 equals to R2. So because your R of Z2 is the position of your mirror M2, so that curvature is R2. Similarly R of Z1, radius of curvature of mirror M1 at position Z1. that is nothing but minus r1. So now we can write from this one minus r1 equals to, so r of z1 equals to minus r1, that equals to, you send the z1 inside, so z1 plus 1 z1 gets cancelled, so this whole term becomes k square by z1. Similarly, r of z2 equals to z2 plus k square by z2. Okay, so now these are your minus r1 and r2, and we know that your z2 minus z1 is the cavity length, that is nothing but L, and k square is pi square omega naught power 4 by lambda square. By solving these three equations, we will get W naught power 4 is equals to lambda square L square by pi square 1 minus zeta 1 zeta 2 into zeta 1 zeta 2 divided by zeta 1 plus zeta 2 minus 2 zeta 1 and zeta 2. So where zeta 1 is defined as 1 minus L by R1 and zeta 2 is defined as 1 minus L by R2. Okay, if you substitute this expression, you will get expression in terms of L and R1. So for simplicity, I am defining this 1 minus L by R1 as zeta 1 and 1 minus L by R2 is defined as zeta 2. So you will end up with this expression. So now from this expression, once you know the W naught, we know the formula how to get W of Z. So W of Z is your beam size changes as you propagate away from your focal region. So your W of Z is depending upon your W naught and the position where you are measuring. So from that equation, we have discussed that equation in our previous classes. You substitute this W naught in that equation, then you will get W square of position at Z1 is equals to lambda L by pi zeta 2 by 1 minus zeta 1 zeta 2 into zeta 1 of whole power 1 by 2. Similarly, you will get for the position Z2, so that means this is the beam sizes at the mirror M1 and mirror M2. So now this is the beam size, the W naught, you send this 4 into other side going to be 1 over like whole term whole power 1 by 4. So that is nothing but beam size at the focus, and this is the beam size at the mirror M1 and this is beam size at mirror M2. So I am calculating beam size of at mirror M1 and M2. So that this is the expression you will get for beam size W square of Z2 equals to lambda L by pi zeta 1 by 1 minus zeta 1 zeta 2 into zeta 2 whole power 1 by 2. For the Gaussian mode should satisfy this condition. So in the resonator, these two Gaussian modes to sustain within the cavity, it has to satisfy that your zeta 1 and zeta 2 should be lie within 0 to 1. If it exceeds or lesser than the 0, then this Gaussian mode cannot sustain. That means that cavity becomes unstable. So now this is the condition for the stable resonator. So generally people call this is the stable resonator condition. So your zeta 1 and zeta 2 is nothing but 1 minus L by R1 into 1 minus L by R2. This product has to be lie within the limits of 0 and 1. Okay, if it should be less than or equals to, like 0 is less than or equals to zeta 1 and zeta 2 and less than or equals to 1. So this is the stability condition for a Gaussian mode to sustain in a laser cavity. So otherwise we don't get a stable resonator condition for a Gaussian mode. Okay, so now we are trying to plot zeta 1 versus zeta 2, and so these are the positions of 1, 1, minus 1 and minus 1 in this axis, and this two deviates, like these two curves will define the boundary of stable and unstable conditions. So now for this, the area which is covered in a green color, these are stable resonators. If zeta 1 and zeta 2 will falls within the 0 to 1 region. So these are all points. You take any point in this curve within this green color region, these are all stable condition. So if you make a resonator, okay, if you make a resonator with this zeta 1 and zeta 2 falls within the green curve, they gives a stable Gaussian mode to oscillate within the cavity. So you will get a stable resonator. Now these red regions are unstable. If you make your resonator which falls in these regions, they cannot maintain the Gaussian mode to oscillate within the cavity. So it leads to unstable condition. So you will get unstable resonator. Okay. So now if you see, there are special points, like in this case you have seen it at 1, your zeta and zeta 2 at 1, and zeta 1 and zeta 2 at 0, their product, and zeta 1 and zeta 2 at -1. So these are the special points what we talk about. So that is, one is a planar condition. So what is your planar? Means your R1 and R2 are infinity. Now if you, in this expression you substitute your R1 equals infinity, what happens? This whole term becomes 0. You substitute R2 equals infinity, this whole term is 0. So your zeta 1 equals to 1 and your zeta 2 equals to 1. The product will be zeta 1 and zeta 2 equals to 1. Now you see your zeta 1 is 1, your zeta 1 is 1, and your zeta 2 is 1. Okay, so that gives you your planar condition. You make your resonator with a different radius of curvature. If you get a zeta 1 and zeta 2 equals to 1, that gives you your planar surfaces. So the both mirrors are planar. And now the other condition is confocal condition. So the confocal conditions gives you your zeta 1 0 and your zeta 2 is 0. So how you get zeta 1 and zeta 2 0? For example, now if we case your R1 and R2 equals to L. That's what we have discussed in the morning session. Your R1 equals to R2 equals to L. What happens? So L by L, that gets cancelled. You will get 1 minus 1, that equals to 0. Similarly, L by L, you will get 1 minus 1. So you will get zeta 1 is 0 and zeta 2 is 0. This is a confocal configuration of the resonator for a two spherical mirrors. And similarly, you can achieve same configuration for your planar surface as well as one of the spherical mirror. So now this radius of curvature is equals to length of the cavity, and this radius of curvature equals to infinity. Now R1 is infinity, R2 equals to L. Now you substitute in this condition, R1 is infinity, right? So R1 is infinity means this becomes 0, and now your R2 is L, that gives you 0. Now your zeta 1 and zeta 2 becomes, the product of zeta 1 zeta 2 becomes 0. So your zeta 1 and zeta equals 0, that gives you this point again. So now this is again a confocal configuration for planar and spherical mirror. So now if it is a confocal condition, your beam width is a shared focus, right? Now if you see, the focus will be at this mirror, and for this mirror also focus at this point. So that is a shared focus between these two mirrors. So that is our confocal condition for the both configurations. If we make any configuration, if we get our zeta 1 and zeta 2 equal to 0, that is our confocal condition. That means the focus is shared with the two mirrors. Now the other condition, the third point is concentric. The concentric means your zeta 1 and zeta 2 product becomes -1. Okay, so that means that how you get -1? So your concentric condition, like in the morning session we already discussed what is the concentric condition is your R1 equals to R2 equals to L by 2, right? If R1, the radius of curvature of mirror M1 and the radius of curvature of mirror M2, that equals to L by 2. So now you substitute this condition here, you will get R1 equals to L by 2. That means your 2 will go up, so L gets cancelled. You will get 1 minus 2. That means -1 you will get in the first here, and also -1 here. You will get 1. Okay, so you will get the product is 1. So that means your product is equal to 1. Okay, so now that is the condition. Your zeta 1 is -1, your zeta 1 is -1, your zeta 2 is -1. You will get the condition of zeta 1 and zeta 2 equals to 1. That is your concentric configuration. Okay, so these are the different configurations of your resonator. Okay, but this curve you call the stability curve or a stability diagram for a stable resonator. So we are worrying about the Gaussian mode because all our applications we are using a Gaussian pulses. For example, right now in the current technology in optical communications we are using Gaussian modes. Okay, as well as in the research purpose, in the industrial purpose we are using Gaussian modes. So more than 90% of usage of your lasers are Gaussian modes. Okay, so that is the reason we have to study and understand the Gaussian mode or TM00 mode of the laser beams.